Tonight, we're going to meet a star so large that our entire inner solar system could disappear inside it. It is called Stephenson 218, a distant red supergiant hidden behind thick clouds of dust roughly 19,000 light-years from Earth. Based on the most widely cited estimates, its radius may be more than 2,000 times greater than that of our own star. Place it at the center of the solar system, and its outer layers could reach roughly as far as Saturn. Mercury would vanish first, then Venus, Earth, Mars, the asteroid belt, and Jupiter. Even Saturn would sit near the edge of an enormous glowing atmosphere stretching almost 1 billion miles from the star's center. And yet, there is something strange about calling Stephenson 218 the biggest star ever discovered. Astronomers cannot simply photograph its edge and measure it. Its atmosphere is diffuse. Its distance is uncertain. Even its membership in the star cluster, used to estimate that distance, has been questioned. So tonight, we're going to find out how astronomers measure something this enormous. Why the biggest stars are not actually the most massive stars. How giants like Scuti and Canis Majoris lost their place at the top of the list, and whether Stephenson 218 truly is the largest star we have ever found. Before we continue, if you enjoy these quiet journeys through space, you can like the video or subscribe to the channel. It helps more people find these stories, and it lets us keep exploring the universe together. The number most often attached to Stephenson 218 is about 2,150 solar radii. A solar radius is simply the distance from the center of our own star to its visible surface, about 696,000 kilometers. Multiply that by a little more than 2,000, and the estimated radius of Stephenson 218 becomes roughly 1.5 billion kilometers. That is close to 10 astronomical units. 1 astronomical unit is the average distance between Earth and the center of our solar system, about 150 million kilometers. Earth therefore sits at 1 astronomical unit. Jupiter averages a little more than 5. Saturn averages about 9.5. Under the famous estimate, the atmosphere of Stephenson 218 would reach almost to the region where Saturn travels around our system. The volume becomes even more extreme. Volume does not increase in direct proportion to radius. If a sphere becomes twice as wide in radius, its volume becomes 8 times greater. Push the radius beyond 2,000 times that of our star, and the resulting volume approaches 10 billion times as much space. That does not mean Stephenson 218 contains the mass of 10 billion stars. It does not. In fact, that difference between size and mass will become one of the strangest parts of its story. Most of this enormous object is an extended, extremely thin stellar envelope rather than a uniformly dense ball of material. Even the word surface needs some care. There is no solid boundary where the star simply stops. A red supergiant becomes thinner and thinner as you move outward through its atmosphere until the stellar material gradually gives way to gas and dust surrounding it. Depending on exactly what astronomers measure and at which wavelength they observe, the apparent edge can shift. So the image of a perfectly defined red sphere reaching Saturn is useful for understanding the scale. But the real object is considerably messier. And from Earth, almost none of this scale is obvious. Stephenson 218 does not hang prominently in our night sky. It lies in the direction of Scuti, looking through one of the crowded, dusty regions of the Milky Way. Between us and the star are enormous amounts of interstellar material, capable of absorbing and scattering its light. That obscuration is part of the reason its story begins not with someone noticing an impossibly large red star in a telescope, but with astronomers learning how to look through the dust of our own galaxy. The real Stephenson 218 sits in a much less convenient place than the scale comparison suggests. From Earth, we see it in the direction of Scutum, a small constellation lying almost directly along the broad band of the Milky Way. That location matters. When astronomers look towards Scutum, their line of sight passes through the crowded disk of our galaxy. This flattened region contains most of the Milky Way's stars, along with enormous clouds of gas and microscopic grains of solid material. Looking through it is very different from looking above or below the galactic plane, where the view contains much less intervening matter. The dust causes the greatest difficulty. Interstellar dust is made from tiny solid grains, commonly containing silicate minerals, carbon-rich material, and compounds that can acquire coatings of ice inside cold molecular clouds. Individual grains are usually far smaller than anything visible to the naked eye. Yet a cloud containing enough of them can block the combined light of millions of distant stars. Visible light traveling toward Earth repeatedly encounters these grains. Some photons are absorbed. Others are scattered away from their original path. Astronomers call the resulting loss of light extinction. The effect also changes color. Shorter visible wavelengths are generally scattered and absorbed more efficiently than longer red wavelengths. A distant star behind substantial dust can therefore appear both dimmer and redder than it otherwise would. This effect is known as interstellar reddening. For a red supergiant, which is already naturally cool and red compared with many other massive stars, separating the star's intrinsic color from the effects of intervening dust becomes particularly important. An incorrect estimate of that extinction can eventually affect calculations of temperature and luminosity, which then feed directly into an estimate of stellar size. The region around Stephenson 218 is heavily obscured because we are looking through a long stretch of the inner galactic disk. Along that path are molecular clouds containing the cold gas from which stars can form, older stellar populations, and dense concentrations of material associated with the Milky Way's spiral structure. This difficult sightline helps explain why the stellar grouping associated with Stephenson 218 entered astronomy relatively recently. In 1990, American astronomer Charles Bruce Stephenson published a catalogue of previously overlooked open clusters and possible stellar groupings. Among them was the concentration now known as Stephenson 2. At first, the important discovery was the group itself. Astronomers had identified a region containing stars that appeared associated with one another on the sky. Determining exactly what kinds of stars were present required more observations. Later work showed that the region is unusually rich in red supergiants. A red supergiant represents a late evolutionary stage reached by some massive stars. These objects have exhausted the hydrogen supply in their central regions and undergone major changes inside. Their outer envelopes expand until the stars can become hundreds of times wider than our own star, while their exposed outer layers cool to temperatures of only a few thousand degrees. Finding many red supergiants concentrated in one region is valuable because this stage does not last very long. Massive stars themselves survive for only millions to tens of millions of years, and the red supergiant phase occupies a relatively small portion of that lifetime. A group containing numerous examples gives astronomers the chance to compare stars that may have formed under broadly similar conditions and at roughly similar times. Differences between them can reveal how stellar mass loss, temperature, and evolutionary state change as massive stars approach the ends of their lives. Stephenson 2, therefore, became scientifically interesting, well before anyone could confidently place one of its apparent members at the top of a largest star ranking. The original catalogue did not contain a measurement showing that Stephenson 218 extended almost to Saturn's orbit. Detecting a source and determining its true physical dimensions are separated by several additional steps. The dust blocking visible light had already dictated where those steps would have to begin. Astronomers needed radiation capable of passing through the obscuring material more easily, carrying information from stars that ordinary visible light observations struggled to reach. That meant looking beyond the colors human eyes can see. Infrared observations changed the view almost immediately, because infrared light has longer wavelengths than visible light. Those longer wavelengths interact differently with the dust spread through the galactic plane, allowing a much larger fraction of the radiation from hidden stars to reach our telescopes. The difference can be dramatic. A cloud that makes a distant star extremely faint at visible wavelengths can become partly transparent in the near-infrared. Astronomers still have to correct for the remaining dust, but they gain access to sources that would otherwise be buried behind the Milky Way's darker lanes. This became especially useful during large surveys of the sky. One of the most important was the 2-micron all-sky survey, which began observations in 1997. The project used 2 telescopes, one at Mount Hopkins in Arizona and another at Cerro Tololo in Chile, to map the entire sky at 3 near-infrared wavelengths. The survey eventually catalogued hundreds of millions of point sources. Many were ordinary stars, but its infrared sensitivity made it particularly valuable in crowded and dusty regions toward the inner Milky Way. Objects that blended into obscured fields in visible light photographs became much easier to separate and measure. Red supergiants are well suited to this kind of observing. Their outer layers are cool by stellar standards, often only a few thousand Kelvin. A large fraction of their radiation, therefore, emerges at red and infrared wavelengths. Dust surrounding the stars can also absorb shorter wavelength radiation and release that energy again in the infrared. Later, observatories extended this view. The Spitzer Space Telescope launched in August 2003 and observed the universe primarily in infrared light. Its instruments could study wavelengths much longer than those used by the 2-micron all-sky survey, making Spitzer especially effective at examining cool dust, embedded stars, and crowded regions of the galactic disk. For an object such as Stephenson 218, these observations provide several different kinds of information. An image can reveal where the source appears relative to neighboring stars and clouds. In a dense field, that positional information helps astronomers identify which point of light belongs to which catalog entry. Photometry measures how bright that source is. Astronomers record how much radiation reaches a detector through carefully defined wavelength ranges. Repeating those measurements can also reveal whether the star changes brightness over months or years. Spectroscopy goes further by separating the incoming radiation according to wavelength. Instead of measuring only how much light arrives, a spectrograph spreads that radiation into a detailed spectrum. Specific atoms and molecules leave recognizable features in that spectrum. Some wavelengths are absorbed more strongly than others, producing dark bands or narrow lines. Their positions can reveal chemical composition, while their relative strengths help constrain temperature and other atmospheric conditions. Infrared spectrographs on large ground-based telescopes became particularly valuable for red supergiants because they could collect detailed spectra in wavelengths where galactic dust causes less interference. Even with these instruments, Stephenson 218 does not turn into a photograph showing a clean circular surface. At roughly 19,000 light-years, under the commonly adopted distance, its apparent diameter is extraordinarily small. A star can possess a physical radius comparable to several planetary orbits and still occupy only a tiny angle in the sky when viewed from that far away. Most observations therefore treat it much more like a point source than a resolved globe. The instruments collect radiation coming from the star and its surrounding material. From that radiation, astronomers can estimate brightness, temperature, motion, and atmospheric properties. Those measurements eventually allow them to infer a physical radius, although the star itself may never appear as the enormous red sphere suggested by scale illustrations. Infrared astronomy therefore solves only part of the problem. It allows astronomers to detect and characterize a source hidden behind galactic dust, while physical size remains dependent on another quantity that infrared brightness alone cannot provide. A distant powerful star and a closer, weaker star can send almost the same amount of radiation to Earth. To separate those possibilities, astronomers need to know how far the light has traveled. Once astronomers can measure the radiation arriving from Stephenson 2.18, distance becomes the number that gives those measurements physical meaning. From Earth, a telescope records what astronomers call apparent flux. This is the amount of energy from the star that reaches a given area of the detector each second. A distant star can have a low apparent flux even while producing an enormous amount of energy, simply because its radiation has spread across an ever larger region of space during the journey toward us. The star's total energy output is called its intrinsic luminosity. To calculate that luminosity from the flux measured at Earth, astronomers need a reliable distance. The connection follows the inverse square law. Imagine radiation spreading outward from a star across the surface of an expanding sphere. Double the distance from the star, and the same energy is spread across 4 times as much area. Move 3 times farther away, and it spreads across 9 times the area. This means distance errors grow quickly when astronomers work backward from observed brightness. If a star turns out to be farther away than expected, it must be intrinsically more luminous to produce the same measured flux at Earth. A higher luminosity can then imply a larger radius when temperature is taken into account. For nearby stars, one of the cleanest ways to determine distance uses a small geometric effect called parallax. As Earth travels around its orbit, astronomers observe a nearby star from slightly different positions roughly 6 months apart. Against much more distant background objects, the nearby star appears to shift by a tiny angle. Measuring that angle creates a triangle whose baseline is known from the size of Earth's orbit. Geometry then gives the distance. The effect becomes extremely small for distant stars. A star 10 parsecs away has a parallax of 1/10 of an arcsecond. An arcsecond is only 1/3600th of a degree. At distances of several thousand parsecs, the shift shrinks to tiny fractions of that already small angle. The European Space Agency's Gaia spacecraft was built to make measurements on exactly these scales. Gaia launched in December 2013 and spent more than a decade repeatedly measuring the positions, motions, brightnesses, and other properties of an enormous fraction of the Milky Way's stellar population. Its catalogs contain astrometric information for well over 1 billion sources. Astrometry means measuring positions and motions on the sky with extreme precision. Even Gaia faces difficult targets. Stephenson 2.18 is very distant, heavily obscured, intrinsically variable, and surrounded by an extended atmosphere. A red supergiant can also have an uneven surface whose brightest regions change over time. At extreme precision, those shifting bright areas can complicate the apparent position of the star. Astronomers therefore use additional evidence when studying distant stellar groups. For Stephenson 2, commonly adopted distances have fallen around 5.5 to 6 kiloparsecs. 1 kiloparsec is about 3,260 light-years, placing that range at roughly 18,000 to 20,000 light-years from Earth. Researchers can estimate such a distance by studying many stars thought to belong to the same group. Proper motion measures how a star drifts across the sky. Radial velocity measures motion toward or away from Earth, usually through small shifts in known spectral lines caused by the Doppler effect. Stars born together should generally share related motions through the galaxy. Their measured brightnesses and spectra can also be compared with stellar models appropriate for their evolutionary state. Dust adds another correction. Astronomers estimate how much radiation has been removed and how strongly the spectrum has been reddened along the line of sight. Underestimating that extinction makes the star appear intrinsically weaker than it really is. Overestimating it pushes the inferred luminosity upward. These pieces eventually feed into the famous size estimate for Stephenson 218. The observed radiation is corrected for dust, a distance is adopted, the luminosity is calculated, and the star's temperature is estimated from its spectrum. The radius comes later from combining those quantities. A distance near 19,000 light-years, therefore, sits near the foundation of the entire record claim. That becomes especially important because Stephenson 218's relationship with the surrounding stellar cluster is less secure than its name might suggest. The name Stephenson 218 makes the star sound like an ordinary member of Stephenson 2, one object among many, inside the same stellar group. In practice, astronomers have had to be more cautious. A true star cluster is more than a group of points that happen to appear close together in the sky. Its members generally formed from the same large cloud of gas and move through the Milky Way together. Their positions can spread out over time, but their motions should still show a family resemblance. Astronomers test that relationship in several ways. One is proper motion, the slow drift of a star across the sky. Another is radial velocity, which measures motion along our line of sight, either toward Earth or away from it. Radial velocity comes from the Doppler effect. If a star is moving away from us, recognizable lines in its spectrum shift slightly toward longer wavelengths. Motion toward us shifts those lines toward shorter wavelengths. The displacement can be converted into a speed, often measured in kilometers per second. For stars belonging to the same cluster, those velocities should fall within a reasonably consistent range after accounting for measurement uncertainty and the internal motions of the group. The object, popularly called Stephenson 218, is also listed in the astronomical literature as Stephenson 2 DFK1. The letters come from a later catalogue of red supergiants in the region. Studies of the Stephenson 2 population found that DFK1 does not fit perfectly with some of the stars regarded as secure members of the cluster. In particular, its measured radial velocity has raised doubts about whether it shares the same motion through the galaxy. That creates several possibilities. It may still be associated with the wider stellar population around Stephenson 2. Crowded regions of the inner Milky Way can contain extended groups and nearby structures that do not fit neatly into a single compact cluster. It could also sit somewhat in front of the main cluster or farther behind it, while appearing close to the same stars from our viewpoint. Projection makes this common in astronomy. Two stars separated by thousands of light-years along our line of sight can appear nearly beside each other in a photograph because the image compresses three-dimensional space onto the flat sky. That distinction matters enormously for Stephenson 218. If the star is assumed to share the distance of Stephenson 2, astronomers can adopt a distance around 5.5 to 6 kiloparsecs and use that value when calculating its luminosity. If the star actually lies closer, the same amount of radiation reaching Earth would correspond to a lower intrinsic luminosity. A lower luminosity, combined with the same estimated temperature, would produce a smaller calculated radius. A greater distance would push the calculation in the opposite direction. This is how uncertainty in one measurement moves through the rest of the analysis. Distance affects luminosity. Luminosity then becomes one of the quantities used to infer radius. The uncertainty does not make Stephenson 218 an ordinary star. Its spectrum still identifies an extremely luminous, cool, evolved massive star surrounded by the complications expected in a red supergiant environment. The issue is the precision of the record attached to it. A commonly repeated radius near 2,150 times that of our own star depends partly on placing DFK1 at a particular distance and assigning it a particular luminosity. Those choices are reasonable enough to produce a serious record holder candidate, while the uncertainty remains large enough that the ranking should not be treated like a precisely measured world record. Astronomers therefore have to reconstruct the star from several imperfect pieces of evidence. Once a distance is adopted, the radiation itself carries the next part of the calculation. Its total brightness and its temperature can be combined to estimate how much surface area the star must have, turning a faint infrared point in Scutum into an object with a radius measured in billions of kilometers. With a plausible distance in hand, astronomers can begin turning the radiation from Stephenson 218 into a physical model of the star. The first step is estimating its total luminosity, meaning the amount of energy it emits across all wavelengths every second. Visible light alone would give a badly incomplete answer, because this is a cool red supergiant hidden behind heavy dust. Astronomers therefore work toward what is called bolometric luminosity. The word bolometric simply means that the energy is counted across the star's full spectrum rather than through one narrow band of visible light. That requires several corrections. Radiation absorbed by interstellar dust has to be estimated. Infrared emission from materials surrounding the star must be separated as carefully as possible from radiation produced by the stellar atmosphere itself. The adopted distance then converts the measured flux at Earth into the star's true energy output. Under commonly used assumptions, Stephenson 218 has been assigned a luminosity of roughly several 100,000 times that of our own star. One widely cited value is around 440,000 solar luminosities. The next important quantity is temperature. Astronomers estimate this from the star's spectrum. When its radiation is separated by wavelength, the result contains broad molecular features and narrower absorption lines formed in its outer atmosphere. Cool red supergiants show strong signatures from titanium oxide. This molecule can survive in stellar atmospheres with temperatures of only a few thousand Kelvin. At much higher temperatures, the molecular bonds would be broken apart. Other molecules, including carbon monoxide, can also appear in spectra of cool evolved stars and help astronomers constrain the conditions in their extended atmospheres. For Stephenson 218, some of the estimates that produce its most extreme published size place its effective temperature in the low 3000 Kelvin range. Effective temperature has a specific meaning. A real red supergiant atmosphere contains hotter regions, cooler regions, moving gas, and extended layers. Astronomers use effective temperature as the temperature a simpler idealized surface would need in order to radiate the same total amount of energy per unit area. This combination produces the remarkable result. A surface at roughly 3000 to 3500 Kelvin does not radiate as intensely from each square meter as the surface of our own star, whose effective temperature is about 5770 Kelvin. Yet Stephenson 218 is thought to release hundreds of thousands of times more total energy. That energy has to come from an enormous radiating area. The relationship is described by the Stefan-Boltzmann law, developed from 19th century work by physicists Joseph Stephan and Ludwig Boltzmann. In simple terms, a star's luminosity depends on its surface area and on the fourth power of its effective temperature. That fourth power matters greatly. A modest change in temperature can produce a large change in the amount of energy emitted by each unit of surface. For a relatively cool star to remain extraordinarily luminous, the required surface area grows rapidly. Once astronomers adopt a luminosity and an effective temperature, they can solve that relationship for radius. Using one of the commonly cited combinations, with luminosity around 440,000 times that of our own star, and an effective temperature in the low 3000 Kelvin range, the inferred radius reaches roughly 2,150 solar radii. One solar radius is about 696,000 kilometers. Multiplying that by 2,150 gives a radius close to 1.5 billion kilometers. The diameter would therefore approach 3 billion kilometers. This is where the Saturn scale comparison comes from. The famous number is therefore the end of a chain of measurements and assumptions. Astronomers measure radiation, estimate how much dust altered it, adopt a distance, infer luminosity, estimate effective temperature from the spectrum, and then calculate the radius required to produce those observed properties. Small changes anywhere in that chain can move the final radius. A hotter temperature reduces the required surface area. A lower luminosity also produces a smaller star. Revised distance estimates can change both the luminosity and the resulting radius significantly. The 2,150 solar radius figure remains useful because it shows what the extreme interpretation of the observations implies. It should be understood as a model-dependent estimate rather than the result of directly seeing two opposite edges of the star. That distinction becomes even more important when we look closely at what astronomers mean by an edge in the first place. Red supergiants possess atmospheres so extended and diffuse that the boundary between star and surrounding space can shift depending on how it is observed. A radius of roughly 2,150 solar radii sounds precise, but a red supergiant does not have an edge like a rocky planet. Earth has a surface you can stand on. Jupiter has a visible cloud deck that gives observers a fairly clear reference level. A star is different because it is made entirely of gas and plasma, with density decreasing gradually as you move outward. Astronomers usually define a star's apparent surface using the photosphere. The photosphere is the layer where light finally becomes able to escape into space without being repeatedly absorbed and scattered by the material above it. Deeper inside the star, photons interact so often with matter that the interior is effectively opaque. Higher up, the gas becomes thin enough for radiation to travel outward much more freely. Astronomers describe this using a quantity called optical depth. Optical depth measures how difficult it is for light to pass through a layer of material. A high optical depth means the material is very opaque. As density falls toward the outside of a star, optical depth also falls. The photosphere therefore marks a useful observational boundary. But it is a boundary defined by radiation rather than by a solid change in material. In a compact star like our own, that distinction is easy to overlook because the visible surface appears relatively sharp from a distance. Red supergiants have much more extended atmospheres. Above the conventional photosphere, temperatures can remain low enough for molecules to survive. Titanium oxide is especially important because its broad absorption bands are prominent in the spectra of cool red supergiants. Carbon monoxide can form farther through the atmosphere as well. In sufficiently cool extended layers, water vapor has also been detected around some evolved giant stars. These molecules occupy gas that is still physically associated with the star, even though it may sit well above the layer used to define the traditional stellar radius. Farther outward, conditions become cool enough for solid dust grains to form. Oxygen-rich red supergiants commonly produce silicate dust. That material can be carried away by stellar winds and collect into a circumstellar envelope, meaning a cloud of gas and dust surrounding the star itself. By that point, identifying one exact location where the star ends becomes increasingly artificial. The atmosphere might extend for several times the photospheric radius in some wavelengths. Dust can continue much farther. Gas flowing outward can remain detectable across distances measured in many astronomical units. This also means that a red supergiant can appear to have slightly different dimensions depending on how it is observed. Visible light tends to emerge from one set of atmospheric depths. Near-infrared radiation can probe somewhat different layers. Certain molecular absorption bands can make the apparent diameter larger because the molecules responsible for those features exist above the main photosphere. Astronomers sometimes measure an angular diameter, meaning the tiny apparent width of the star on the sky. That angular diameter can change with wavelength because each wavelength becomes opaque at a different depth in the atmosphere. The effect has been observed clearly in nearby red supergiants where interferometers have enough resolution to begin resolving the stellar disk. Their apparent sizes can shift depending on whether the observation samples the relatively clean continuum between molecular bands or radiation strongly affected by extended atmospheric material. Stephenson, 218, is much farther away, making that kind of direct measurement especially difficult. Its commonly quoted radius, therefore, comes largely from luminosity and effective temperature rather than from a sharply resolved edge. Time adds another complication. Red supergiants are variable. Their outer layers expand and contract. Giant convection cells change across the surface, and mass can be lifted into the surrounding atmosphere. Over months or years, the effective temperature and brightness can shift enough to alter the inferred radius. A single number, therefore, describes one interpretation of the star under a particular set of assumptions and observations. The physical object itself is continually changing. This is important when imagining Stephenson 218 filling the solar system. The famous comparison does not describe a perfectly smooth red sphere ending at a clean boundary near Saturn. The outer regions would become progressively thinner, with glowing gas giving way to extended atmospheric material and then to circumstellar matter farther out. Even so, the photospheric scale implied by the largest published estimates remains extraordinary. Using that reference level, the star's nominal radius reaches into a region of space normally occupied by entire planetary orbits. At the commonly cited radius, the photosphere of Stephenson 218 would extend for almost 10 astronomical units from its center. An astronomical unit is the average distance between Earth and the center of our solar system, about 150 million kilometers. It provides a convenient ruler here because the scale of this star overlaps directly with the scale of planetary orbits. Earth travels around its orbit at 1 astronomical unit. If Stephenson 218 replaced our own star while keeping the extreme radius estimate, Earth would lie deep inside the stellar envelope, roughly 1/10 of the way from the center to the nominal photosphere. Mars averages about 1.5 astronomical units from the center of the solar system. Its entire orbit would also fit comfortably inside. Farther out, Jupiter travels at an average distance of about 5.2 astronomical units. Even the largest planet in our system would remain only a little more than halfway toward the estimated edge of Stephenson 218. Saturn provides the closest familiar marker for the full scale. Its average orbital distance is about 9.5 astronomical units, or roughly 1.4 billion kilometers. The commonly quoted radius of Stephenson 218 approaches 1.5 billion kilometers. Under those assumptions, the visible stellar atmosphere would reach to approximately the region occupied by Saturn's orbit. This comparison also helps establish what the estimate does not mean. Neptune orbits at an average distance close to 30 astronomical units. It would remain far outside a star, with a radius near 10 astronomical units. Some popular descriptions of Stephenson 218 have stretched the comparison beyond Neptune, but that would require a radius roughly 3 times larger than the famous estimate. The diameter is twice the radius, so a 10 astronomical unit star would measure close to 20 astronomical units from one side of its photosphere to the other. Even light needs a noticeable amount of time to cross that distance. Light travels through space at just under 300,000 kilometers per second. Crossing 1 astronomical unit takes about 8 minutes and 19 seconds. Crossing 20 astronomical units would therefore take approximately 2 hours and 46 minutes. A beam of light sent straight through the center of a hypothetical. Stephenson 218 would begin at one side of the photosphere and reach the opposite side nearly 3 hours later. Travel around the star would take much longer. A sphere with a radius near 10 astronomical units has a circumference of roughly 63 astronomical units. Light following that distance would require about 8 hours and 45 minutes to complete the circuit. Those times apply to light, the fastest thing able to carry information through space. The physical distances become even easier to appreciate when compared with spacecraft. Voyager 1 has been traveling away from the solar system since September 1977. Its speed relative to the Sun is roughly 17 kilometers per second. At that speed, covering a distance equal to the estimated diameter of Stephenson 218 would take several thousand years. Yet even this planetary scale picture can be misleading if we imagine the entire volume filled with material resembling the bright surface of our own star. Near the nominal photospheric boundary of a red supergiant, the gas is extremely thin compared with material deeper inside. Density falls steeply as distance from the center increases. Molecules can form in the extended atmosphere, and farther out, dust can condense within material already being pushed away by stellar winds. Saturn sitting near the commonly cited photospheric radius therefore gives us a useful geometric marker. It does not describe a hard wall of dense, glowing matter at exactly 9 or 10 astronomical units. The immense size comes from an envelope that has expanded to extraordinary distances while becoming increasingly rarefied. That leads to one of the most counterintuitive properties of Stephenson 218. Increasing a sphere's radius by more than 2,000 times increases its volume by almost 10 billion times. The star does not contain anything close to 10 billion times as much matter. Its enormous dimensions are possible because a comparatively modest amount of stellar mass has been spread across a volume large enough to encompass the orbits of several planets. A radius more than 2,000 times greater than that of our own star produces a volume that grows far faster than the radius itself. The reason is simple geometry. The volume of a sphere depends on the cube of its radius. Increase the radius by 2,000 times, and the volume increases by about 8 billion times. Push that radius to roughly 2,150 times the solar value, and the volume approaches 10 billion times as much space. That number can sound as though Stephenson 218 must also contain billions of times more matter. Its actual mass is nowhere near that scale. For evolved red supergiants, the present-day mass can be difficult to determine because the star has already spent part of its life losing material through powerful winds. Estimates also depend on evolutionary models, distance, luminosity, and assumptions about how much mass has already escaped. For that reason, assigning Stephenson 218 one exact mass would create more precision than the observations support. What can be said with much greater confidence is that stars in this evolutionary class contain masses measured in tens of solar masses rather than millions or billions. That creates an extraordinary mismatch between size and substance. A star can occupy a sphere almost 10 billion times greater in volume, while containing only a few tens of times as much mass as the star at the center of our solar system. The explanation lies in how the material is distributed. Most of a red supergiant's mass is concentrated much farther inward than its visible radius suggests. Deep inside, gravity compresses matter to densities and temperatures high enough for nuclear fusion. Moving outward through the star, pressure and density fall dramatically. By the time the outer envelope reaches distances measured in astronomical units, the material has become extremely tenuous. The word envelope refers to the broad outer region surrounding the nuclear burning core. During the red supergiant phase, this envelope expands enormously. The same amount of matter becomes spread across a much larger region, so its density drops. This is why average density can be useful for illustrating the scale, even though it does not describe conditions at any one location very well. Take the total mass of a star, divide it by an enormous volume, and the resulting average can become surprisingly low. Yet the real star is highly uneven. Its core is tremendously denser than the average, while its outermost atmosphere is far thinner. In the most extended layers, individual particles can travel relatively large distances before colliding with others. Gas is still hot by everyday standards, but the amount of matter contained in each cubic meter has fallen dramatically compared with deeper stellar layers. Closer to the photosphere, giant convective motions churn material upward and downward. Above that region, molecules can survive. Farther outward, some of the gas cools enough for dust grains to form before stellar winds carry the material away. The star therefore resembles a compact gravitational center wrapped in an immense, inflated atmosphere whose density fades with distance. That structure allows radius to change far more dramatically than mass. A star does not have to acquire vast amounts of new material to become a red supergiant. Internal changes can cause an existing envelope to expand outward by hundreds or thousands of times. The star becomes physically larger because its outer layers occupy more space. This also explains why a radius record tells us very little about which star contains the most matter. Some stars are born with far greater masses than the ancestors of many red supergiants. Their enormous gravity and intense radiation produce very different evolutionary paths. Many remain much hotter and more compact, while strong stellar winds can strip away their outer layers before they ever develop an envelope as wide as the one associated with Stephenson 218. The biggest star and the heaviest star therefore belong to two different categories of extreme objects. To understand why, we have to leave the swollen red supergiants for a moment and look at stars whose masses reach far beyond anything Stephenson 218 is thought to contain. The distinction becomes especially clear when we compare Stephenson 218 with stars that contain far more matter. One of the best examples is R136A1, located in the 30 Doradus star-forming region of the Large Magellanic Cloud, a small companion galaxy of the Milky Way, about 160,000 light-years away. R136A1 belongs to an exceptionally dense cluster of young, massive stars. Estimates of its present mass remain model-dependent, but they place it comfortably above 100 times the mass of our own star, with some studies suggesting that it may have formed with well over 200 solar masses. Yet its physical radius is nowhere close to that of Stephenson 218. R136A1 is extremely hot. Its surface temperature is measured in tens of thousands of Kelvin, several times hotter than the surface of our own star. That high temperature allows each square meter of its surface to radiate an enormous amount of energy, so the star can be millions of times more luminous without needing an envelope that extends across several astronomical units. This illustrates why stellar records have to be separated carefully. Mass measures how much matter a star contains. Radius measures how far its visible atmosphere extends from the center. Luminosity measures total energy output. Surface temperature describes the characteristic energy of the radiation emerging from the outer layers. A star can rank near the top in one category, while being far less extreme in another. Many of the most massive stars begin their lives as O-type stars. These are hot, blue stars, with surface temperatures commonly above 30,000 Kelvin. Their intense ultraviolet radiation can ionize nearby hydrogen gas, creating glowing regions around young stellar clusters. Their luminosity also produces powerful stellar winds. In very luminous stars, photons streaming outward interact with atoms and ions in the atmosphere. That transfer of momentum can accelerate gas away from the surface. Over hundreds of thousands or millions of years, the cumulative mass loss can become enormous. The process becomes especially important for stars born with the greatest masses. Some lose so much material that their outer hydrogen-rich envelope is stripped away. Deeper layers enriched by nuclear processing become exposed, producing objects known as Wolf-Rayet stars. Wolf-Rayet stars are among the hottest and most wind-dominated stars known. Their spectra often show broad emission lines, formed in fast outflows, moving at hundreds or even thousands of kilometers per second. They can lose mass rapidly enough to alter their entire later evolution. That matters for stellar size, because a vast red supergiant radius requires an envelope capable of expanding. A star that keeps a substantial hydrogen-rich outer layer can undergo dramatic inflation as conditions change in the core. A star that loses much of that envelope early may follow a hotter evolutionary route and never develop a photosphere extending across the equivalent of several planetary orbits. This is one reason the largest stars are not simply the stars that began with the highest masses. Red supergiants generally descend from massive stars, often with initial masses of roughly 8 solar masses or more, although the exact upper range that spends significant time in the red supergiant phase depends on composition, rotation, mass loss, and the details of stellar models. At the very high mass end, strong winds can remove too much material for the star to remain a huge, cool supergiant for long. Stephenson 218, therefore, represents a very different kind of extreme from R136A1. Its extraordinary radius comes from an evolved outer envelope that has swollen to tremendous dimensions. The star did not begin life with a diameter stretching from the center of our solar system toward Saturn. Earlier in its existence, it would have been much smaller, much hotter, and likely much bluer. The enormous red object we see today is the product of changes that occurred after the star had already spent millions of years converting hydrogen into helium deep in its core. As that original fuel supply changed, the balance between gravity, pressure, and energy production shifted with it. Those internal changes are what allowed an ordinary massive star to become one of the largest objects ever associated with a stellar photosphere. Earlier in its life, a star capable of becoming a red supergiant would have looked very different from Stephenson 218 today. It would have been smaller in radius, much hotter at the surface, and probably blue or blue-white. Deep inside, hydrogen nuclei were being converted into helium while gravity continuously tried to compress the star toward its center. For most of a star's life, these opposing effects remain in a long-lived balance called hydrostatic equilibrium. Gravity pulls matter inward, The hot gas and radiation inside the star create pressure that pushes outward. As long as energy production in the core can maintain enough pressure, the star remains relatively stable. In massive stars, hydrogen fusion proceeds especially quickly through a sequence of reactions called the carbon-nitrogen-oxygen cycle. Carbon, nitrogen, and oxygen nuclei act as intermediaries that help combine hydrogen nuclei into helium. The nuclei participating in the cycle are reused, while the overall process converts 4 hydrogen nuclei into 1 helium nucleus and releases energy. The cycle becomes increasingly important at the high core temperatures found in massive stars. That temperature sensitivity has a major consequence. A star with 10 or 20 times the mass of our own star contains much more hydrogen fuel, yet it burns through that fuel far faster. The star at the center of our solar system can remain on the main sequence for roughly 10 billion years. A massive star, destined to become a red supergiant, may spend only several million to a few tens of millions of years in its hydrogen-burning phase, depending on its initial mass and composition. During that period, helium gradually accumulates in the core. Eventually, the supply of hydrogen available for fusion in the central region becomes depleted enough that the structure of the star has to change. Energy production in the core falls, and gravity begins compressing the helium-rich center. Compression raises the core temperature. At the same time, hydrogen fusion continues in a shell surrounding the inert helium-rich core. Shell burning means that the main fusion reactions are now concentrated in a layer outside the center rather than throughout the original hydrogen-burning core. The combination of core contraction and shell burning releases a tremendous amount of energy into the surrounding layers. That energy changes the outer star. The hydrogen-rich envelope begins expanding outward. As it expands, its outer layers cool. The star's effective surface temperature can fall from tens of thousands of Kelvin during an earlier hot phase to only a few thousand Kelvin as a red supergiant. Its color shifts toward orange and red because a cooler stellar surface emits a larger fraction of its visible radiation at longer wavelengths. The total luminosity can remain enormous throughout this transformation. This is possible because luminosity depends on both temperature and radiating area. As the surface cools, the rapidly increasing radius provides vastly more area from which energy can escape. On a Hertzsprung-Russell diagram, which plots stellar luminosity against surface temperature, an evolving massive star can move toward the upper right region. Stars there are both highly luminous and relatively cool, the characteristic territory of red supergiants. The physical transformation is remarkable. A star that once occupied a region comparable to only a fraction of Earth's orbital distance can eventually expand to hundreds or even more than 1,000 times the radius of our own star. In the most extreme estimates for Stephenson 218, the envelope reaches thousands of solar radii. That expansion does not happen because new material has been added. The existing outer layers respond to changes occurring much deeper inside. The core becomes hotter and more compact, while the envelope moves outward and cools. This is why the enormous radius of Stephenson 218 represents a late stage in stellar evolution. Its size records what has happened to the star after millions of years of nuclear burning and structural change. The expanded envelope also creates a new problem for transporting energy. Radiation produced deep inside still has to move through a star whose outer layers now extend across distances comparable to planetary orbits. In those cool, opaque regions, carrying energy outward by radiation alone becomes inefficient. The envelope begins moving the energy in a much more physical way, through enormous rising and sinking currents of stellar material. Those rising and sinking currents are convection, and inside a red supergiant they can operate on a scale that is difficult to reproduce anywhere else in astronomy. Energy leaving the nuclear burning regions of a star does not travel outward in the same way through every layer. In hotter, less opaque regions, much of it moves by radiative diffusion. Photons are repeatedly absorbed and re-emitted as they work their way through dense, stellar material. A photon may travel only a short distance before interacting with another particle. Its overall movement is outward, but the route can involve an enormous number of individual steps. Farther into the cool, expanded envelope of a red supergiant, radiation becomes less efficient at carrying the required energy. The gas is comparatively opaque, and the temperature changes sharply with depth. Under those conditions, convection becomes increasingly important. Convection moves energy by moving the material itself. Hotter gas below becomes buoyant and rises. As it reaches higher layers, it expands and cools while releasing energy. Denser, cooler material then sinks back into the star, allowing the cycle to continue. The same basic process occurs in a pot of heated water, although a red supergiant turns it into something vastly larger. Our own star has convection near its outer layers, producing the familiar granular pattern seen in high-resolution solar images. Individual granules there are typically around 1,000 kilometers across and survive for only minutes. On red supergiants, the cells can become enormous. Betelgeuse provides one of the clearest nearby examples. It lies roughly several hundred light-years away in Orion and has been observed with high-resolution telescopes and interferometers that can begin to resolve structures across its surface. Instead of a perfectly uniform disk, observations show bright and dark regions that change with time. Some of these features are thought to be associated with giant convective structures, carrying hot material upward through the atmosphere. The cells predicted by three-dimensional models can occupy a substantial fraction of the star's radius. A red supergiant may therefore have only a relatively small number of very large convective regions dominating its visible surface at any one time. Antares, the bright red supergiant in Scorpius, has shown similar complexity. In 2017, astronomers using the Very Large Telescope Interferometer produced detailed measurements of gas motions across Antares. The observations indicated an extended, turbulent atmosphere with material moving farther from the stellar surface than simple convection models had expected. This matters because convection in a red supergiant does more than transport energy. Large rising cells can disturb the photosphere, alter local temperature, and contribute to asymmetries in the star's brightness. Material pushed high enough may enter regions where pulsation, radiation pressure, or dust formation helps carry it even farther outward. A star with a radius measured in hundreds or thousands of solar radii therefore cannot be treated as a perfectly smooth sphere with identical conditions at every point. That creates a challenge for stellar models. Traditional one-dimensional models describe a star as a series of spherical layers. Each layer has values for temperature, density, pressure, and composition, and the computer calculates how those properties change from the center outward. This approach is extremely useful for following stellar evolution over millions of years. It becomes less complete when a surface is dominated by structures that are neither small nor spherical. A giant convective cell can make one region hotter and brighter than another. Gas may rise farther on one side of the star. Shocks can move through the atmosphere. The apparent center of light can even shift as bright structures change position. Researchers therefore use three-dimensional radiation hydrodynamic simulations to study these outer layers in more detail. Radiation hydrodynamics combines the motion of gas with the transfer of radiation through that gas. Computers follow changing density, temperature, velocity, and energy flow across a three-dimensional grid, allowing enormous convective structures to form naturally rather than forcing the star into perfectly spherical layers. These simulations help explain why real red supergiants can show irregular surfaces, extended atmospheres, and changing brightness patterns. For Stephenson 218, the distance prevents astronomers from mapping its convective surface with anything close to the detail possible for Betelgeuse. Its classification tells us, however, that the same basic physics should operate within its enormous cool envelope. The star's outer layers are therefore in constant motion, even during periods when its overall radius seems roughly stable. On longer timescales, that stability weakens further. The envelope can expand and contract as a whole, changing the star's brightness, temperature, and measured size over periods lasting hundreds of days or more. The motion inside a red supergiant does not stay confined to individual convective cells. Over longer periods, the star itself can swell and contract. Astronomers see this through long-period variability, meaning changes in brightness that unfold over hundreds or even thousands of days. Red supergiants often show more than one timescale at once, and the pattern can be irregular because several physical processes are overlapping. One of those processes is radial pulsation. During a radial pulsation, large portions of the stellar envelope move outward and then inward again. Gravity pulls the expanded material back toward the center, while pressure changes inside the star help drive the next motion. The result is a slow oscillation in radius rather than a perfectly fixed stellar size. For a red supergiant, a single cycle can last many months. The changing radius also affects temperature. As the outer layers expand, they generally cool. During contraction, they can become somewhat hotter. Because the amount and color of radiation emitted by a stellar surface depends strongly on temperature, even modest changes can alter the star's measured brightness. This variation is layered on top of the convection already moving through the atmosphere. Large convective cells can brighten one part of the visible surface while cooler regions become dimmer. Their appearance and position can change without the entire star expanding by the same amount. Astronomers sometimes describe this irregular component as stochastic variability, meaning that it is driven partly by complex motions that do not repeat with the precision of a clock. Betelgeuse offers a useful nearby example. The red supergiant in Orion has been monitored for well over a century, and its brightness changes on several timescales. One prominent variation lasts roughly 400 days, while a much longer cycle extends across several years. Researchers continue to study how much of that behavior comes from pulsation, convection, atmospheric changes, and mass loss. Betelgeuse also demonstrated how difficult it can be to interpret one unusually deep change in brightness. Between late 2019 and early 2020, the star underwent what became known as the Great Dimming. Its visible brightness fell dramatically. Detailed observations later showed that cooling in part of the photosphere, together with dust formed from previously ejected material, played an important role. That event did not require the entire star to change in one simple way. It showed how pulsation, convection, and material above the photosphere can combine to alter what an observer on Earth measures. The same general caution applies to Stephenson 218. If its outer layers expand, the radius associated with the photosphere can increase. A contraction can reduce that value. Changes in temperature also affect a radius inferred from luminosity through the Stefan-Boltzmann relationship described earlier. An observation made during one phase of the star's variability may therefore produce a somewhat different estimate from an observation made years later. The mechanisms behind red supergiant pulsations are still an active area of research. In many variable stars, Changes in opacity can help trap and release energy in a repeating pattern. Red supergiants are more complicated because their enormous convective envelopes, low surface gravity, and extended atmospheres all influence the oscillations. Three-dimensional simulations show that convection itself can excite large-scale motions. Pressure waves move through the envelope, and the atmosphere may respond unevenly across the stellar surface. A single textbook mechanism cannot account neatly for every observed cycle. This matters when a radius is being used to rank the largest stars ever measured. A value such as 2,150 solar radii should not be imagined as a permanent geometric property that remains unchanged year after year. The star's actual atmosphere is moving, and the layer from which most observed radiation escapes can shift with that motion. At these dimensions, even a small percentage change in radius represents an enormous physical distance. A 5% variation in a 10 astronomical unit radius would amount to roughly half an astronomical unit, comparable to 75 million kilometers. Repeated expansion also has consequences beyond changing a measurement. Each outward motion lifts material farther into regions where gravity is weaker and temperatures are lower. Some of that gas can cool enough for molecules and dust grains to form. Once material reaches those heights, radiation and stellar winds have a better chance of carrying it away permanently. The same instability that makes the star breathe can therefore help dismantle its outer layers over time. Once material is lifted high enough above a red supergiant, returning to the deeper atmosphere becomes progressively harder. The reason begins with surface gravity. Gravity depends on both mass and distance from the center. Stephenson 218 may contain tens of times the mass of our own star, yet its outer atmosphere is spread across a radius measured in astronomical units. At those distances, the gravitational pull acting on each parcel of gas is much weaker than it would be near a compact stellar surface. Escape velocity falls as well. This is the speed an object would need to leave the star permanently without additional propulsion. Near the dense inner regions, gravity binds material strongly. Farther out in the swollen envelope, matter needs less additional energy to escape. Convection and pulsation can provide part of that energy. A large convective upwelling may push hot gas toward the photosphere. A pulsation can then carry part of the surrounding atmosphere farther outward. These motions do not automatically eject the gas, but they can lift it several stellar scale heights above its previous position. Astronomers sometimes describe this process as atmospheric levitation. The word simply means that material is being supported or pushed temporarily above the region where it would otherwise settle. At greater distances from the star, the temperature drops. This changes the chemistry. Close to the photosphere, temperatures of several thousand Kelvin are too high for most solid particles to survive. Farther out, gas may cool enough for atoms and molecules to combine into microscopic grains. Stephenson 218 belongs to the broad class of oxygen-rich red supergiants. Around stars of this type, astronomers commonly detect silicate-rich dust containing elements such as silicon, magnesium, and oxygen. Dust formation becomes important because solid grains interact strongly with radiation. Photons leaving the star carry momentum. When they are absorbed or scattered by dust grains, some of that momentum is transferred to the grains. The result is radiation pressure, a small force on each individual particle that becomes significant when a star is producing hundreds of thousands of times the luminosity of our own star. Dust grains moving outward collide with surrounding gas and can help drag it along. The full mechanism behind red supergiant winds remains an active area of research. Convection can lift material, pulsation can extend the atmosphere, and radiation acting on newly formed dust can help accelerate some of that matter farther from the star. The relative importance of each process changes with temperature, chemistry, and stellar structure. Over time, the escaping material forms a stellar wind. For a red supergiant, the wind can carry away substantial amounts of mass over thousands of years. The loss is often uneven. Some material leaves relatively steadily, while larger episodes can eject dense clumps or shells. Nearby red supergiants show what this can produce. Canis Majoris, roughly a few thousand light-years from Earth, is surrounded by arcs, knots, and clouds of expelled material. Observations suggest that portions of this structure were launched during separate episodes rather than through one perfectly steady wind. Betelgeuse provides a more recent example of localized mass loss. Observations associated with its great dimming indicated that a substantial amount of material had been expelled from part of the star before cooling and helping form dust along our line of sight. Modern radio telescopes can examine this material in extraordinary detail. The Atacama Large Millimeter, Submillimeter Array in northern Chile observes wavelengths produced by cold gas and dust around evolved stars. Its collection of dozens of antennas can act together as a much larger virtual telescope, allowing astronomers to map molecular gas flowing through circumstellar envelopes. Infrared observatories complement those measurements by tracing warmer dust closer to the star. These observations repeatedly show that red supergiant mass loss can be asymmetric. Material may leave more strongly in one direction, producing clumps and arcs instead of smooth spherical shells. The surrounding cloud can eventually extend far beyond the photosphere. By then, the matter is no longer participating in the star's normal atmospheric circulation. It has become part of the circumstellar environment, expanding outward while the star continues evolving inside. Every successful ejection slightly reduces the mass available to hold the envelope together. This creates a powerful feedback near the extreme end of stellar evolution. Expansion places the surface farther from the center, weakening its gravitational binding. Atmospheric motions can then lift material more easily, and some of that material escapes permanently. A red supergiant approaching enormous dimensions is therefore also gradually dismantling itself. That process places a practical restraint on how far stellar inflation can continue. Beyond some point, the same conditions that allow the envelope to grow also make it increasingly difficult for the star to keep that envelope attached. The weakening grip of the outer envelope places one practical limit on stellar growth, although astronomers do not have a single number that marks the largest radius a star can ever reach. Several different pieces of physics begin pushing against extreme expansion at the same time. One of them is known as the Hayashi limit, named after Japanese astrophysicist Chushiro Hayashi. In the 1950s and 1960s, Hayashi helped establish how fully convective stars behave on the Hertzsprung-Russell diagram, the chart astronomers use to compare stellar luminosity and surface temperature for a star of a given mass and chemical composition. There is a cool boundary beyond which a stable, fully convective configuration becomes very difficult to maintain. Red supergiants sit close to this cool edge. Their surface temperatures are commonly only around 3,500 Kelvin, sometimes somewhat lower, depending on how the atmosphere is modeled. As a red supergiant expands and cools, its internal structure changes in ways that resist unlimited movement towards still lower temperatures. The Hayashi limit, therefore, helps explain why red supergiants gather within a particular region of the Hertzsprung-Russell diagram, rather than spreading indefinitely toward cooler and larger configurations. A separate constraint comes from radiation pressure. Every photon leaving a star carries momentum. In sufficiently luminous stars, That outward flow can exert considerable force on matter in the atmosphere. The Eddington luminosity describes the point where outward radiation pressure acting on material can balance the inward pull of gravity under a simplified set of assumptions. The Eddington concept is especially important for very massive stars because luminosity rises rapidly with mass. Its relationship with maximum radius is indirect. Reaching an Eddington-like condition does not assign one particular diameter to a star. It tells astronomers when radiation begins having enough influence to make parts of the atmosphere increasingly difficult to bind. Opacity matters here because radiation can exert force only when it interacts with matter. Opacity measures how strongly material absorbs or scatters radiation. Different atoms and ions dominate that interaction at different temperatures inside a star. In some layers, high opacity allows radiation to push particularly strongly against the surrounding gas. That can contribute to envelope inflation and instability. Observations reveal another boundary, called the Humphreys-Davidson limit. Astronomers Roberta Humphreys and Chris Davidson recognized in the late 1970s that the Hertzsprung-Russell diagram contains very few extremely luminous cool stars above a certain region. Stars massive enough to reach those luminosities appear to become unstable and shed material before spending long periods as enormous red supergiants. This helps explain an apparent paradox. Adding more initial mass does not guarantee a larger final radius. At sufficiently high luminosity, powerful winds and episodes of severe mass loss can remove much of the envelope that would otherwise expand. Chemical composition influences the outcome as well. Astronomers describe the abundance of elements heavier than helium using the term metallicity. A star with more of these elements generally has more atoms and ions capable of interacting with radiation. That can strengthen certain stellar winds and alter how quickly mass is removed. Metallicity also changes opacity inside the envelope, affecting the temperature and radius a stellar model predicts. Convection adds further complexity. Giant cells move energy and matter through the envelope, while pulsation periodically shifts the atmosphere outward. Computer models have to represent all of these processes over an enormous range of scales, from the compact nuclear burning interior to an atmosphere extending billions of kilometers. The treatment of mass loss is especially important. Stellar evolution calculations use what are called mass loss prescriptions, mathematical relationships estimating how quickly a star loses matter under particular conditions. Different prescriptions can produce noticeably different late-stage masses and radii. For that reason, theoretical calculations can produce red supergiant radii, reaching a few thousand solar radii under some conditions without identifying one universally accepted maximum value. Stephenson 218 therefore occupies a particularly interesting part of this landscape. A radius near 2,150 solar radii would place it among the most extremely inflated stellar configurations discussed in astronomy. Such a size pushes toward conditions where low surface gravity, strong convection, atmospheric instability, and continuing mass loss all become increasingly important. The star can remain enormous for a time, although the same physics that creates the swollen envelope also works continuously to reshape and remove it. This helps explain why lists of the largest known stars have changed so often. The objects themselves are difficult to define and variable, while improved measurements can shift their calculated radii by hundreds of solar radii. Several stars once presented as record holders have already moved down that list as astronomers learned more about their distances and atmospheres. Betelgeuse is a useful place to begin because it is one of the few red supergiants bright enough to be familiar even outside astronomy. It marks the shoulder of Orion and lies only a few hundred light-years from Earth. Its radius is usually placed at several hundred times that of our own star, with the exact value changing depending on wavelength, distance estimate, and the phase of its variability. Even at that scale, Betelgeuse would extend well beyond the orbit of Mars if placed at the center of our solar system. For much of modern astronomy, stars like Betelgeuse helped establish what a red supergiant could look like. As telescopes improved, even larger candidates began appearing. Canis Majoris became one of the most famous. It lies several thousand light-years away in the constellation Canis Major, and is surrounded by an enormous cloud of material expelled during earlier episodes of mass loss. Historical estimates sometimes assigned it a radius approaching 2,000 solar radii or more, placing it among the most extreme stars then known. Improved distance measurements and more detailed atmospheric models later changed that picture. Modern estimates commonly place Canis Majoris closer to roughly 1,400 solar radii, although the exact value still depends on how its extended atmosphere is defined. That remains an extraordinary size. It simply no longer occupies the same position on many record lists that it once did. The difficulty comes partly from its surroundings. Dust and gas around the star absorb, scatter, and re-emit radiation. If some of that circumstellar emission is attributed directly to the photosphere, the inferred luminosity can become too large. A larger luminosity then pushes the calculated radius upward. Scuti followed a similar path. This red supergiant lies in the constellation Scutum, along another dusty line of sight through the Milky Way. For years, popular descriptions gave it a radius near 1,700 times that of our own star, which helped make Scuti perhaps the best-known answer to the question of the largest star in the universe. That number depended heavily on the adopted distance. When the distance changes, luminosity changes with the square of that distance. A revised distance therefore changes the radius inferred from the star's brightness and effective temperature. Measurements in the Gaia era have complicated older assumptions about Scuti's distance and motion. Different analyses have produced substantially different physical parameters, and its former position as an obvious record holder has weakened. NML Cygni offers another example. It is an extremely luminous cool supergiant in Cygnus, surrounded by dense circumstellar material and located several thousand light-years away. Estimates have placed its radius well above 1,000 solar radii, making it another serious member of the historical group of largest known stars. Its environment makes the calculation difficult for familiar reasons. Dust alters the incoming spectrum. Distance carries uncertainty. The atmosphere itself is extended rather than sharply bounded. This pattern repeats across the record books. Interferometry has improved angular diameter measurements for some nearby giants by combining light from multiple telescopes. Gaia has transformed stellar distance measurements across much of the Milky Way. Better infrared observations have allowed astronomers to separate stellar radiation from surrounding dust more carefully. Each improvement can move a star up or down the ranking. A revised temperature of only a few hundred Kelvin matters because temperature enters the luminosity-radius relationship so strongly. A modest change in distance alters luminosity immediately. A better model of circumstellar dust can remove radiation once assumed to come directly from the star. The name attached to the top of the list therefore reflects the measurements available at a particular time. Betelgeuse remains enormous. Canis Majoris remains one of the most extreme red supergiants known. Scuti remains physically vast. Their changing positions tell us more about improving astronomy than about the stars somehow shrinking between observations. Stephenson 218 sits inside this same history. Its commonly cited radius may eventually survive better measurements, or future work may reduce it, just as earlier estimates were revised for other giants. And farther away, in another galaxy, astronomers have recently begun resolving the environment of an extreme red supergiant in a way that would have been impossible only a generation ago. A particularly useful comparison lies far beyond the Milky Way, inside one of our galaxy's nearest large companions. The Large Magellanic Cloud is a small satellite galaxy, roughly 160,000 light-years from Earth. It is visible from the southern hemisphere as a faint patch of light, yet it contains enormous stellar nurseries and some of the most massive evolved stars astronomers can study outside our own galaxy. Among them is WOHG 64, an exceptionally luminous red supergiant surrounded by a thick envelope of gas and dust. The star has been studied for decades. Earlier observations already suggested an extreme size, with estimates on the order of roughly 2,000 times the radius of our own star under some models. Its dusty surroundings also made it a valuable example of the heavy mass loss expected near the end of red supergiant evolution. In November 2024, the European Southern Observatory announced a major step forward. Using the Very Large Telescope Interferometer in Chile, astronomers produced what the observatory described as the first close-up image of a star located outside the Milky Way. That achievement is especially striking because WOHG 64 is almost 10 times farther away than the commonly adopted distance to Stephenson 218. The image was made possible by interferometry. A single telescope is limited partly by the diameter of its mirror. Larger apertures can distinguish finer details because they provide greater angular resolution, meaning they can separate objects or structures that appear extremely close together on the sky. Interferometry combines light collected by telescopes, separated from one another. The arrival of the light waves is measured with extraordinary precision and then combined so that the array can resolve details comparable to those accessible with a much larger telescope, spanning the distance between the individual instruments. At the Very Large Telescope Interferometer, light can be collected by several separate telescopes at the Paranal Observatory in Chile's Atacama Desert. For the new observations, astronomers used an instrument called gravity, which can combine near-infrared light from 4 telescopes simultaneously. Earlier observations of WOHG 64 had already been made with the interferometer in 2005 and 2007, using an older instrument that combined light from 2 telescopes. Those measurements revealed information about the dusty environment, but did not produce the kind of resolved image achieved later. The 2024 result showed something unexpected. Instead of appearing as a simple symmetrical glow, WOHG 64 was surrounded by a bright elongated structure described as an egg-shaped dusty cocoon. A fainter elliptical feature farther out may represent the inner region of a larger dusty structure, although additional observations are needed to establish its shape securely. The cocoon provides a direct view of material recently expelled from the star. Comparisons with earlier observations also indicated that WOHG 64 had become noticeably dimmer over roughly the previous decade. Researchers suggested that newly ejected dust could be responsible for part of that fading by absorbing more of the radiation traveling toward Earth. The change is significant because red supergiants can spend thousands of years shedding their outer layers before core collapse. Human observers usually see only a tiny fraction of that evolution. Detecting substantial change across about 10 years provides a rare glimpse of an extreme star altering its surroundings on a timescale comparable to a human career. The distorted shape may also contain information about how the material was expelled. A strongly asymmetric ejection could produce an uneven cocoon. Researchers have also considered the possibility that an unseen companion star could influence the geometry, although that interpretation remains uncertain. WOH G64, therefore, deserves attention alongside the largest star candidates in our own galaxy, while its exact position on a radius leaderboard remains model-dependent. Its greater importance here comes from what astronomers can now observe directly. A distant red supergiant, once represented mainly by measurements of brightness and spectra, can begin to reveal actual structure around itself. Dust that previously complicated estimates becomes something that can be mapped. Changes inferred from older measurements can be compared with newer, resolved observations. That development points directly back towards Stephenson 218. Its famous radius still depends heavily on distance, temperature, luminosity, and atmospheric modeling. Improving the record will require observations capable of separating those quantities as independently as possible, ideally while tracking how the star changes over time. A stronger measurement of Stephenson 218 would require several independent pieces of evidence to agree with one another. Distance is still the foundation. The Gaia mission has provided the most precise astrometric map of the Milky Way ever assembled, measuring positions and motions for well over 1 billion stars. For difficult objects such as red supergiants, its long-term value also comes from the wider stellar population around them. Proper motions can help identify which stars move together, while radial velocities measured from spectra reveal motion toward or away from Earth. Together, those measurements can strengthen or weaken the case that Stephenson 218 belongs to the same stellar population as Stephenson 2. A more secure distance would immediately improve the luminosity estimate. The next step is measuring how much energy the star actually emits. Astronomers observe across many wavelengths because a cool red supergiant sends a large fraction of its radiation into the infrared. They then estimate the bolometric flux, meaning the total amount of radiation reaching Earth after accounting for energy spread across the spectrum. Dust complicates this calculation because some radiation is absorbed and then re-emitted at longer wavelengths. Researchers use radiative transfer models to simulate that process. These models follow radiation as it passes through gas and dust, allowing astronomers to estimate how much of the infrared glow comes directly from the star and how much comes from material surrounding it. Temperature requires another independent measurement. Infrared spectroscopy can reveal molecular features associated with cool stellar atmospheres. Comparing those features with atmospheric models helps constrain the effective temperature, which strongly affects the radius inferred from luminosity. The most direct improvement would come from measuring the star's angular diameter. Angular diameter is simply how wide an object appears on the sky. For something 19,000 light-years away, even a star, billions of kilometers across, covers an extraordinarily tiny angle. Interferometry offers one of the best ways to reach that scale. Instead of relying on a single mirror, an interferometer combines light collected by telescopes separated across a large distance. The effective resolving power can approach that of a telescope with a diameter comparable to the separation between them. If astronomers can measure a reliable angular diameter and combine it with an independently determined distance, the physical radius follows from geometry. Red supergiants make even that measurement complicated because their apparent diameters can change with wavelength. Molecular layers may make the star look larger in one infrared band than in another. Dust can contaminate the signal farther out. A useful campaign would therefore observe the star repeatedly across several wavelengths. This also helps with variability. Stephenson 218 is expected to change over time like other red supergiants. Multi-epoch observations meaning observations taken at many different times, can track shifts in brightness, temperature, and apparent size across months or years. That prevents one unusually expanded or contracted phase from being mistaken for a permanent radius. Several major observatories can contribute pieces of this work. The James Webb Space Telescope is especially powerful in the infrared and can study heavily obscured stellar environments with far greater sensitivity than many earlier missions. Its instruments can help characterize dust, molecular emission, and the energy distribution surrounding evolved massive stars. Ground-based telescopes provide another advantage: extremely high angular resolution. The European Southern Observatory is building the extremely large telescope in Chile with a primary mirror 39 meters across. Once operating, it will collect far more light and resolve finer detail than existing single optical and infrared telescopes. Future improvements in infrared interferometry could push resolution even farther. No single observation is likely to settle the record by itself. A trustworthy radius would come from agreement between distance measurements, spectroscopy, bolometric flux, atmospheric modeling, and angular size. That is what makes the uncertainty surrounding Stephenson 218 useful rather than frustrating. Each uncertain quantity corresponds to something astronomers can measure more carefully. The star may eventually turn out to be smaller than the famous estimate. Better observations could also strengthen the case for an extraordinary radius near its current value. Either result would tell us something important about how far red supergiant envelopes can expand. And while those measurements may improve over years or decades, the star itself continues changing on timescales set by processes deep below its visible atmosphere. Far beneath the dust, pulsations, and convective surface lies a compact core where the remaining nuclear fuel is being consumed at an accelerating pace. Beneath the enormous convective envelope, the final stages of a massive star unfold in a region that occupies only a tiny fraction of its visible size. After hydrogen in the central core is exhausted, helium becomes the next major fuel. At temperatures around 100 million Kelvin, 3 helium nuclei can combine through the triple alpha process to form carbon. Additional reactions produce oxygen. Helium burning lasts far less time than hydrogen burning. A massive star may spend millions of years fusing hydrogen, then only hundreds of thousands of years or less working through helium, depending on its mass and detailed structure. Once helium becomes depleted in the center, gravity contracts the core again. Compression raises the temperature until carbon can begin fusing. Carbon burning requires temperatures of roughly 600 million Kelvin and can produce elements including neon, sodium, and magnesium. The pace now changes dramatically. For a massive star, carbon burning may continue for hundreds to thousands of years. The exact duration varies greatly between stellar models, but it is already brief compared with the millions of years spent on the main sequence. After carbon comes neon burning. At core temperatures above roughly 1 billion Kelvin, energetic photons become capable of breaking apart some neon nuclei. The resulting particles participate in reactions that help build heavier elements, especially oxygen and magnesium. This stage may last only around a year, or a few years in some massive star models. Oxygen burning follows at temperatures approaching 2 billion Kelvin. Oxygen nuclei collide and fuse into heavier products such as silicon, sulfur, and related elements. By this stage, the star can move through a major fuel supply in a matter of months. Silicon burning is faster still. At temperatures of several billion Kelvin, the core enters a complicated network of nuclear reactions that gradually drives its composition toward iron group elements. Depending on the star, this final major burning stage can last only days. A star whose outer atmosphere changes over periods of hundreds of days can therefore have a core progressing through an entire late nuclear burning stage during a single week. Part of the reason for this acceleration is that heavier fuels provide progressively less usable energy for supporting the star. Another important effect is neutrino cooling. Neutrinos are extremely light particles that interact only weakly with ordinary matter. At the enormous temperatures reached during advanced burning, reactions inside the core produce vast numbers of them. Most escape almost immediately, carrying energy away. The hotter the core becomes, the more important these losses become. To replace that escaping energy, the star has to burn fuel even faster. That speeds the evolution further, raising temperatures and pushing the core toward the next stage. Near the end, the interior develops what astronomers often describe as an onion shell structure. Iron group material accumulates near the center. Surrounding layers can contain silicon burning farther out, with oxygen-rich material beyond that. Still farther from the center sit shells, containing products left from earlier carbon and helium burning. These shells are packed inside a region tiny compared with the full radius of a red supergiant. The star may extend across billions of kilometers, while the advanced nuclear reactions controlling its fate occur deep within the central portion of the object. For Stephenson 2:18, we cannot identify the exact burning stage taking place at this moment. Its distance prevents astronomers from directly observing the core. The surface properties tell us that it is an evolved massive star, but they do not reveal whether its center is currently burning helium, carbon, oxygen, or a later fuel. Even estimates of its present mass and evolutionary state remain uncertain enough that assigning a precise countdown would be unjustified. What stellar models do show is the direction of travel. Each major stage requires a hotter core. The remaining fuel is consumed more quickly, and neutrino losses become increasingly severe. The enormous outer envelope can continue changing slowly, while the central evolution accelerates beneath it. Eventually, the sequence reaches iron group nuclei. Fusion up to this region of the periodic table has helped support the star by releasing energy. Once the core becomes dominated by iron group material, continuing ordinary fusion can no longer provide the same source of pressure support. At that point, the process that has balanced gravity for millions of years is approaching its end. Once an iron-rich core has formed, the star has reached a fundamental boundary in nuclear physics. Fusion releases energy when lighter atomic nuclei combine into more tightly bound nuclei. This advantage continues through much of the periodic table until the reactions approach the iron group. Around iron and nickel, nuclei sit near the peak of what physicists call the nuclear binding energy curve. Building substantially heavier nuclei by ordinary fusion requires energy instead of releasing enough to support the star. The iron-rich core, therefore, continues growing as surrounding shells deposit additional material onto it. Gravity compresses the center, while the electrons inside the dense matter provide an important source of pressure. This support has a limit. For a cold, idealized core supported mainly by electron degeneracy pressure, the famous Chandrasekhar mass is about 1.4 times the mass of our own star. Real pre-supernova cores are hotter and structurally more complicated, so collapse cannot be reduced to one exact mass threshold. The Chandrasekhar scale still marks the basic physical regime where electron pressure can no longer hold gravity back indefinitely. Conditions then deteriorate rapidly. At densities far beyond anything found in ordinary matter on Earth, energetic electrons are forced into atomic nuclei and combine with protons. The reaction produces neutrons and neutrinos. This process is called electron capture. Removing free electrons weakens the pressure supporting the core. At the same time, extremely energetic radiation begins breaking some heavy nuclei apart. That process consumes energy that could otherwise resist compression. Gravity gains control. Once the runaway collapse begins, the central region contracts in well under a second. Matter can fall inward at tens of thousands of kilometers per second. A core that had spent millions of years evolving reaches its decisive transition almost instantaneously. As density rises toward that found inside an atomic nucleus, roughly hundreds of trillions of grams per cubic centimeter, the behavior of matter changes. Protons and electrons have increasingly been converted into neutrons, producing the beginnings of a proto-neutron star. The word proto simply means that this compact object has only just formed and is still extremely hot. The innermost collapsing material suddenly becomes much harder to compress. The core rebounds, launching a shock wave outward into material that is still falling inward. For many years, astronomers hoped this bounce might explain the supernova explosion by itself. Computer simulations showed that the situation is more difficult. The outward moving shock loses enormous amounts of energy. Heavy atomic nuclei ahead of it are broken apart, which consumes energy. Neutrinos carry additional energy away. Within a relatively short distance, the shock can stall instead of continuing cleanly through the entire star. This stalled shock problem became one of the central challenges in explaining core collapse supernovae. Modern models give neutrinos an important role in reviving the explosion. The newborn proto-neutron star releases an extraordinary flood of neutrinos as it cools and contracts. Roughly 99% of the gravitational binding energy liberated during core collapse ultimately escapes through these particles. Most neutrinos pass directly through the surrounding matter, but a small fraction deposit energy behind the stalled shock. That fraction can matter. Three-dimensional simulations also show turbulent motions developing in the material surrounding the new compact core. These motions keep some gas in the neutrino-heated region longer, improving the chance that enough energy will be absorbed to help the shock begin moving outward again. The exact explosion mechanism remains an active area of research, and different progenitor stars can behave differently. If Stephenson 218 retains a substantial hydrogen-rich envelope when its core eventually collapses, the resulting event would most naturally fall within the broad family of Type II supernovae. Once the explosion is launched successfully, the shock still has an enormous distance to travel. For a red supergiant with a radius approaching the famous 10 astronomical unit estimate, the surface could lie nearly 1.5 billion kilometers from the center. A shock, moving through the envelope at thousands to tens of thousands of kilometers per second, could require many hours to roughly a few days to reach the outermost layers, depending on how its speed changes through the star. Eventually, the shock reaches material thin enough for trapped radiation to escape rapidly. This moment is called shock breakout. The star can brighten dramatically as energy that began with a collapse deep in the center finally reaches the surrounding universe. The scale reversal is extraordinary. An envelope, once stretching across billions of kilometers, has been transformed by events that began inside a core small enough to become one of the most compact objects known. After the shock has crossed the envelope, the star separates into two radically different futures. At the center, the remnant may be compressed to the scale of a city. A typical neutron star measures only about 20 to 25 kilometers across. That is a remarkable contraction from a red supergiant radius measured in billions of kilometers. Inside a neutron star, matter reaches densities comparable to those found in atomic nuclei. Electrons and protons have largely combined into neutrons, and the remnant is supported by a combination of neutron degeneracy pressure and the strong nuclear force that acts between particles at extremely short distances. A neutron star can contain more mass than our own star, inside a sphere small enough to fit across a major metropolitan area. This outcome is not guaranteed for Stephenson 2.18. If the collapsing core ends up too massive to remain stable as a neutron star, gravity can continue compressing it. Once no known pressure can halt the collapse, a black hole forms. The dividing line depends on more than the star's total mass before the explosion. Astronomers have to consider the structure of the core immediately before collapse. How much of the envelope was lost during earlier stellar winds, and how energetic the explosion becomes. Some material launched outward may also fail to escape completely. This returning debris is called fallback. It can add mass to the compact remnant after the initial explosion, potentially turning a newly formed neutron star into a black hole. Farther out, most of the former envelope follows a completely different path. Supernova ejecta can race into space at thousands to tens of thousands of kilometers per second. Material that once moved slowly through the atmosphere and stellar wind is suddenly accelerated outward by the passage of the explosion. The ejecta carry the chemical history of the star with them. Carbon and oxygen produced during earlier nuclear burning can be expelled into space. Deeper layers contain silicon, sulfur, calcium, and iron group elements created during later stages. The explosion itself can also alter the composition. As the shock passes through different shells, temperatures rise sharply for a short time. This explosive burning can create additional elements and isotopes that were not present in the same quantities before core collapse. The details depend strongly on temperature, density, and how long each layer remains hot. Astronomers once described ordinary supernovae as the main factories for nearly every element heavier than iron. The modern picture is more complicated. Some of the heaviest nuclei require a process involving extremely rapid captures of neutrons. This is called the rapid neutron capture process, often shortened in scientific literature to the R process. Observations and theoretical work now show that neutron-star mergers are major sites for this process. The merger detected through gravitational waves in August 2017 produced electromagnetic signatures consistent with the creation of heavy elements through rapid neutron capture. Certain rare stellar explosions may contribute as well. That means elements such as gold, platinum, and uranium should not all be attributed automatically to an ordinary red supergiant supernova. Their cosmic origins can involve multiple types of violent events. For Stephenson 2.18, the safer prediction is that its death would eject large amounts of material enriched by millions of years of stellar fusion, while the exact inventory of the heaviest nuclei would depend on the details of the explosion and remnant. The expanding debris eventually forms a supernova remnant. As the ejecta collide with surrounding gas, shock waves heat the material and cause it to glow at radio, optical, and X-ray wavelengths. The remnant can expand for thousands of years before gradually merging with the interstellar medium, the diffuse gas and dust spread between stars. The expelled material does not remain isolated forever. Over much longer periods, enriched gas can mix into molecular clouds. Gravity may eventually compress parts of those clouds until new stars form. Dust grains and heavier elements can become incorporated into rocky planets, asteroids, and other solid bodies. The final result is another reversal of scale. A star, once large enough to encompass planetary orbits, may leave behind a remnant only a few tens of kilometers across, while its former envelope spreads outward across light years. That entire life cycle brings us back to the number that started the story. After tracing how these stars are measured, how they inflate, why they lose mass, and how they eventually collapse, the label largest star ever discovered, becomes far more conditional than it first appeared. Stephenson 218 remains extraordinary, but the exact size of that record still depends on measurements that astronomy continues to refine. The most widely repeated estimate for Stephenson 218 places its radius near 2,150 times that of our own star. Under that interpretation, the photosphere would reach almost 10 astronomical units from the center. A diameter close to 20 astronomical units would place the star among the most physically extended stellar objects ever discussed in the astronomical literature. That number remains extraordinary, but every part of it depends on earlier measurements holding together. The adopted distance has to be close to correct. If Stephenson 218 truly lies around 5.5 to 6 kiloparsecs away, its observed brightness corresponds to the enormous luminosity used in the largest radius estimates. Its relationship with Stephenson 2 therefore matters. The alternative designation DFK1 refers to the same object, and studies of its radial velocity have made cluster membership less secure than the familiar name suggests. A different distance would change the luminosity calculation. Temperature matters just as much. The most extreme radius estimates use an effective temperature in the low 3000 Kelvin range. Raising that temperature means each square meter of the stellar surface radiates more energy, reducing the amount of surface area required to explain the observed luminosity. Dust introduces another layer of uncertainty. The line of sight towards Scutum crosses a crowded, heavily obscured part of the galactic plane. Interstellar dust removes radiation before it reaches Earth, while material expelled by the star can absorb stellar energy and radiate it again in the infrared. Correcting for both effects influences the total luminosity assigned to the star. Then there is the boundary itself. A red supergiant possesses an extended atmosphere rather than a permanent geometric edge. Molecular layers can sit above the conventional photosphere. Pulsation moves parts of the atmosphere outward and inward over time. Different wavelengths become opaque at different depths, allowing the apparent radius to change depending on how the observation is made. All of this makes one perfectly exact radius inappropriate for an object like Stephenson 218. The strongest conclusion is still impressive. Stephenson 218 is an exceptionally luminous, cool, evolved massive star associated with some of the largest radius estimates ever applied to a known star. Its famous value, near 2,150 solar radii, makes it one of the leading candidates for the largest known red supergiant. Its precise position at number 1 remains open to revision. Astronomy has already watched this happen to other giants. Scuti became famous through estimates approaching 1,700 solar radii, before revised distances changed its inferred properties. Canis Majoris once appeared even larger in some older calculations, while improved modeling of its atmosphere and surrounding material brought many modern estimates closer to roughly 1,400 solar radii. Those changes did not make the stars less remarkable. They showed how much the ranking depends on the quality of the measurements. Stephenson 218 may follow the same history. Better distance constraints could reduce its estimated radius. More sophisticated atmospheric models could alter the effective temperature. Future observations might instead strengthen the case that it really does occupy a photospheric region approaching 10 astronomical units. There is also no guarantee that the eventual record holder is one of the stars already receiving the most attention. Much of the inner Milky Way is difficult to survey because our viewpoint lies inside the galactic disk. Dust clouds hide distant stars at visible wavelengths, and crowded fields can place enormous numbers of sources within a small patch of sky. Infrared surveys have revealed populations that earlier generations of astronomers could barely study. Improved interferometry can begin separating structures around individual giant stars. Future telescopes with larger mirrors and better angular resolution will push farther into regions where the largest evolved stars remain difficult to characterize. Some candidate may already be present in an astronomical catalogue with an uncertain distance or poorly measured temperature. A star currently treated as one more infrared source could eventually receive a better spectrum, a more secure distance, or an angular measurement sharp enough to reveal that its atmosphere extends farther than anyone expected. Stephenson 218 therefore represents something more interesting than a permanent trophy at the top of a list. It shows how astronomers can take a faint, heavily reddened point of light, almost 19,000 light-years away, and reconstruct a physical object whose atmosphere may span billions of kilometers. For now, that reconstruction places Stephenson 218 among the most enormous stars humanity has ever identified. And, somewhere behind the dust of the Milky Way, the object that eventually replaces it may already be shining.